Okay, well, thank you for coming. I'm going to go ahead and share my screen here. And again, all of the notes are online if you also wanted to download and get a copy there. So I'll just start off, of course, as usual. I'll just make a few quick announcements. Then also, I want to try to do a review of what we did on Monday. And then we'll start to discuss some new stuff today. I also want to say a little bit about some of the problems that we'll have to do for the problem solving session. I should say really the problem set on Friday. So Monday's lesson is on YouTube now. So if you do want to go ahead and watch that, hopefully everything should be easy to find. Also, remember that I'll have office hours at the usual time, so right after class today from 11 to 12, and then also in the afternoon from 4 to 5. For the mentor sessions, Sarish is still holding them Sunday, Monday, Tuesdays, and Thursdays from 6 to 8 p.m. And then finally, in terms of the problem sets and homework assignments, the next homework assignment is due today, so please try to post it online into Sakai by, I'll say, 5 p.m. Pacific. It doesn't really matter the naming scheme that you use for it. I think that some of you may have seen that I've kind of gone back in and I've just changed some of the naming. So for example, homework set number 10 is literally what I've written here. I just have it so that the titles all look like homework set number 10 in this way. This is just so that I can kind of keep track a little bit in terms of what's there. What I have been doing is taking what's in your folders, making a copy of the assignment, sending that to the graders. They're then going to grade it, and then I'll put back a copy of that back into your folder. So that way I want to make sure that there isn't any issue of like what you have in your folder getting lost or deleted or corrupted. And I have copies of everything sitting on my computer locally as well. So hopefully there won't be any issues about any assignments being lost. But please try to upload assignment number 10 by 5 p.m. today. If you have any troubles at all, just send me an email. You can also feel free to send me the homework assignment by email. Problem set number 5 will be done in class. That means here online on Friday. So we're just going to try to play around with it and see how it goes. What I'm hoping to do is if we have some volunteers here, I'll just have you go ahead and share your screens and work it out that way. There apparently is a whiteboard feature that is in Zoom, and I'll kind of show this here. If you go to share screen, then you can actually pull up a whiteboard, and I'm just going to just like write a couple of silly things here. Right. So if you don't really feel comfortable kind of working out everything on the screen, I believe that there's a way that you can have the whiteboard here just to go to your tablet and you can write it out this way. If you also just wanted to write it on a sheet of paper and show it, that's perfectly fine. Again, we'll just try to figure out ways to get this to work, but I am hoping that you all will feel comfortable in doing some of the presentations for some of the problems on Friday. So any questions about any of these announcements here? Okay, great. All right, well, let's try to get started on the new material. So first, let's just do a quick recap. Let's say that our F here is a complete order field, like with the real numbers. So remember that we say that a sequence converges if, given a positive number epsilon, we can find the delta such that xn minus L is less than epsilon whenever n is greater than delta. Right, so that's the simple idea, but we're going to do several examples of this today. So this is what we mean when we say that a sequence converges to F. We say that a sequence has a lower bound, of course, if there's some number a, so that a is less than or equal to xn for all xn in the sequence, and we'll say that it's an upper bound if there's some element b, where b is greater than or equal to xn for all xn's in the sequence. And we'll say that we have a bounded sequence if we can find some element capital M, where this is the case here, right? Where in absolute value, M is greater than or equal to each absolute value of xn in the sequence. Right? So that's just what we mean now by saying that we have a bounded sequence. One of the big theorems that we've seen so far is the monotone convergence theorem. So this says, simply put, if you have a monotone increasing sequence that has an upper bound, then the sequence converges. Right? Similarly, if you have a monotone decreasing sequence and that sequence has a lower bound, then the sequence converges. Okay, so that's the idea of the monotone convergence theorem. Last time we looked pretty heavily at the logistic equation. So that was this equation here, where everything's really defined recursively. So if I have an x0, I can use this here to define x1. Once I have an x1, use that to define an x2, so on and so forth. So we saw a few properties about this sequence last time. First of all, say that my row is a real number between 1 and 4. Then this says that as long as I start in a nice range, x0 between 0 and 1, then everything in the sequence here is between 0 and 1. Right? And in particular, if I started at one of the endpoints, then I'll always be stuck at one of the endpoints. So if my x0 is either 0 or 1 exactly, then my xn's are always going to be 0. But the important statement here is that the logistic equation gives a bounded sequence. Right, so that's really the whole point here, that we really always have a nice bounded sequence. Now, if my real number row is between 1 and 3, then the sequence converges, and actually here's the limit. Right, so if row is small enough, then everything converges very nicely. It's really nothing to worry about. However, if row gets a little bit larger, so now row is between 3 and about 3.45, then the sequence does not converge. However, if I look at either the even subscripts or the odd subscripts, then I find subsequences that do converge. Right, so again, if I just look at the even subscripts or if I just look at the odd subscripts, then I do have a sequence that converges. And actually it converges to one of two numbers. Right, one of these two here. Okay. So again, if my row increases just a little bit larger between 3 and about 3.45, then my sequence doesn't converge. But if I just look at kind of this specified thing with the indices, so even the even indices or the odd indices, then I do find sequences that converge. Okay. We use this to then motivate the idea of a subsequence. So if we're given a sequence A, which we'll write this way here, then a subsequence is really just the subset that is also a sequence. So for example, we can maybe write it this way here. So xn1, xn2. So I can really say that it's just going to be the set of elements where now my subscripts have to come from this set that I'm calling script P. Right, so maybe my subscripts aren't everything. Maybe they aren't all of 0, 1, 2, 3, so on and so forth. They might just be like the even ones. They might be the odd ones. But that's what I mean by a subsequence. Right, that I have an infinite sequence, but I'm only keeping track of certain ones for the subscripts. And so we proved this theorem by Bolzano and Weierstrass that says as long as you have a bounded sequence A, then you have a convergent subsequence. Right, so again, every bounded sequence will have a convergent subsequence. Okay. All right, so any questions on any of these topics that we've covered so far? All right. Now we know in dealing with sequences that if they converge, so let's say maybe that they approach some limit L, then there's this philosophy that the terms in a sequence, since they get closer and closer to L, they actually have to get closer and closer to each other, right? If we kind of just think about some of the numbers that we've been dealing with, it's clear that when we say things like the xn's tend to a certain number, that really what's happening is that the xn's are getting closer and closer to each other. I mean, they're getting closer and closer to L, but they're still getting closer and closer to each other. So I want to make that more precise in the following proposition. So this says, say that we have a convergent sequence. All right, so my A here is just going to be some sequence that converges. So then I have the following statement. For every positive epsilon, there exists a delta so that xm minus xn is less than epsilon, there should be an epsilon here, whenever m and n are greater than delta. So again, this says that xm minus xn is less than epsilon whenever m and n are greater than delta. So this is this whole thing that the terms in the sequence are getting closer and closer to each other. So if I go far enough out in the sequence, that's what this m and n says here, then my xm and xn have to get really, really close to each other. Right. But again, I want to point out that this here should have been an epsilon. So sorry for that typo. Right. Okay, so let's try to maybe go over the proof of this. What's happening here? So what I'm going to say, let's just fix a positive epsilon. Right? Because kind of remember the way that we always do these proofs is you say let epsilon be given, you then have to choose delta and then prove that everything works. So let's start by saying let epsilon be given. Now, we know that by our assumption, A converges to some limit L. Right? That's my assumption. A converges to some limit L. So given maybe some positive epsilon prime, then we know that we have xn minus L is less than epsilon prime whenever n is large enough. Right? That's just the definition of what it means to converge. Right? So given an epsilon prime, I can find a delta so that xn minus L is less than epsilon prime whenever n is large enough. In particular, remember epsilon prime can be anything. So let's pick epsilon prime to be epsilon over 2. Right? Because again, epsilon prime can be anything we want as long as it's positive. So I'm going to set it equal to epsilon over 2. And if this is the case, then according to what I just said here, then I have xn minus L is less than epsilon over 2, xn minus L is less than epsilon over 2 whenever m and n are greater than delta. So here, just pick capital N to either be m or lowercase n. So again, we're just simply using this idea that it has to converge to L. So if you give me epsilon prime, I can find delta. So now I'm going to tell you, okay, choose epsilon prime to be epsilon over 2. And then if I say that, then I know that these two here have to hold whenever m and n are large enough. Okay. So I want to pause for a minute. Are there any questions on how I'm able to make these statements here? Okay. All right, great. Because we're actually going to use this argument over and over again today. Okay, so we have our delta. So now I claim that the following inequalities hold whenever m and n are larger than delta. So to start with, let's take our xm minus xn, and let's write it this way here. Right, so I'm just simply using the fact that if I take x minus L minus y minus L, that's just x minus y. Right? So I'm just kind of rewriting this difference here in a very clever way. Okay, so that's first statement. Next, let me use the triangle inequality. So now I'm going to say that this here is less than or equal because we had the statement here for the triangle inequality. Right, so again, I can just kind of break it up now as a sum. But now, let's go back and use what we had up above. So I said here, that's less than epsilon over 2. This is less than epsilon over 2. So these two here have to both be less than epsilon over 2. And now, of course, we'll just add these two together. So we just realize that epsilon over 2 plus epsilon over 2 is just epsilon. So what we've shown now is exactly the statement that was here in the proposition. So there exists the delta such that xm minus xn is less than epsilon. So remember, this here was the typo. Whenever m and n are greater than delta. So here I've said, assuming m and n are greater than delta, then my xm minus xn is less than epsilon. Right, that's exactly what we wanted to prove. Okay, so any questions here? Okay, all right, let's keep moving on then. Now I'm going to use this to kind of work in the opposite direction. We'll say that a sequence is Cauchy if, given a positive epsilon, there exists a delta so that this thing here, and again, sorry, this should be epsilon here, this xm minus xn is less than epsilon whenever m and n are greater than delta. Right, so now I'm just kind of using the wording that I just had in the previous proposition. So this is what we mean to say that a sequence is Cauchy. Given a positive epsilon, there exists a delta, says that xm minus xn is less than epsilon whenever m and n are greater than delta. So we're going to prove a couple of things about Cauchy sequences. Say that we do have a Cauchy sequence. So first we're going to prove that this sequence is bounded. Right? So there'll be some m that kind of bounds all the terms. And second, we're going to prove that this sequence is convergent. Right? So these will be our two big statements for the day. So again, given a Cauchy sequence, it is both bounded and convergent. Okay. So let's start with proving the very first one, because actually it turns out that this here is a little bit easier for us to do. What I want to do is find an m such that the xn in absolute value is less than or equal to m for all of the terms in the sequence. Right, so that's what it means to say that here we have a bounded sequence. So to this end, fix an epsilon 0. In practice, you can take epsilon 0 to be the number 1. It doesn't matter. Just fix any number that you want. You can pick it to be 1, you can pick it to be 1/2. Doesn't matter at all. All right, just fix a number. Well then, because the sequence is Cauchy, there exists a delta so that this here is less than epsilon 0 whenever m and k are greater than delta. Right, so again, that's what it means to be a Cauchy sequence. So once I fix my epsilon 0, which could be like the number 1/2, it doesn't matter, just fix it and ignore it. Then there's a delta where we have this case here. xm minus xk is less than epsilon 0 whenever m and k are greater than delta. Right. Now let's make an observation here. Well, let's let k be this specific integer. Right, so k here kind of depends upon delta. So let's just fix it to be this very specific integer. So once we do this, now I'm going to say the following. Let's let m be any number that's greater than or equal to k. Well, the way I've set it up, k is greater than delta. So I'm going to let m be this here. For example, if delta is like maybe the number like 10.5. So if delta is 10.5, the floor is 10, and the floor plus 1 would be 11. So now I'm saying if I want a number greater than 10.5, I might as well start with the number 11. That's all that's saying here. All right, so again, let me choose now m and k, at least m here to be greater than or equal to k. So if this is the case, then this absolute value, I'm going to be a little bit clever and add and subtract k. Right, so again, I'm just going to be a little bit clever, add and subtract k. So now I can use the triangle inequality. So we have this here. And now I realize that I'm dealing with the Cauchy sequence. So this here is less than epsilon 0 plus xk. Now you may look at this and say, this is kind of silly, what's important about it? The important thing to take away here is what's over here on the right does not depend on m. Right, what's over here on the left, this is my x sub m, but what's here on the right does not depend upon m. Because again, I fixed x0, epsilon 0, so that's fixed, that's given. That's like maybe the number 1/2. Once I fix epsilon 0, then delta is fixed. And once delta is fixed, then k is fixed. So epsilon 0 and k, they are fixed at the start. It's m here that's varying. Right? M can be anything, but again, what's over here on the right that doesn't depend upon m, only what's over here on the left, that depends upon m. Okay, all right, so any questions on what we have here? Okay, all right, so again, we have now a statement where over here on the left, this depends on m, but over here on the right, this does not. This is completely independent upon m. We fixed our epsilon 0, we fixed our number k. So now I claim that for all terms in the sequence, xn is less than m. So here's how we'll do this. Well, I know that if m is large enough, then xm is less than this here, which is independent of m. Right, that's if m here is large enough. So now let me take a look at what about the first few. So maybe when m is 1, m is 2, through m is perhaps k minus 1. Those are the ones that are missing from this here. Right, if it's k or larger, that's this part. But the ones that are missing are everything less than k. So kind of the first ones here. Sorry, this should be x0 here. So if I choose m to be this, then m is larger than the first k, and then it's larger than everything else. Right, so again, if I choose m to be this here, it's larger than the first k, and then it's larger than everything else. So m here is larger than everything put together. Right. So any questions here on how we were able to deduce that we have a bounded sequence? All right, I'll pause here for a minute to say that on the problem set that we're going to work on for Friday, they want you to prove something similar. So here what we have is, If A is a Cauchy sequence, then A is bounded. One of the problems wants you to prove if A is a convergent sequence, then A is bounded. And there you can actually modify the proof that I have here. Instead of xk, let this be your limit L. And then if this here is your limit, then you'll actually see here that, again, this is your limit L, this is your limit L. Now there is no k to worry about. So all I have to do is just worry about putting in essentially L plus epsilon naught. All right, so I just want to quickly emphasize here that if you stare at the way that I've done the proof here, this actually will help you solve one of the problems that we're going to do on Friday. All right, so all of this together now does prove that our Cauchy sequence actually is a bounded sequence. Okay, all right, so any questions so far? Okay, all right, let's move here. So now I want to prove that a Cauchy sequence actually converges. And we're going to do this kind of in a couple of parts using some of the results that we had from last time. So remember, using the Bolzano-Weierstrass theorem, we know that A is a bounded sequence. We just proved this. Therefore, A has a convergent subsequence. So let's call that B. Right, that's what the Bolzano-Weierstrass theorem says. Because we have a bounded sequence, it has a convergent subsequence. Let's denote L as the limit of this subsequence, whatever it is. We're going to prove that L is also the limit of our sequence A. Right, so again, L is the limit of this subsequence. We know by the Bolzano-Weierstrass theorem that it exists. So let's show that L is the limit of A. So to this end, I'm going to do almost exactly the same proof that we've been doing all along. Let's say that epsilon here is positive, it's given. Let's denote epsilon prime as epsilon over 2. Now I want to make two observations before I go any further. Observation number 1. A is a Cauchy sequence. So that means I can find a delta 1 so that we have this inequality here whenever lowercase n and capital N are large enough. Right, again, this is what it means to be a Cauchy sequence. So I can find the delta 1, depending, of course, on epsilon prime, where I have this inequality as long as lowercase and capital N are large enough. Okay. Let me make my second observation. Because B is a convergent sequence, we can find a delta 2 so that we have this here now. This is so that my x n k minus L is less than epsilon when I'm looking at my subsequence large enough. Right, my n sub k here corresponds to the subsequence. I have to be very, very careful what terms I'm looking at here. All right. So any questions up to this point? All right, just two observations here. One is for the Cauchy sequence, one is for the subsequence. Okay. All right. So now we should be able to do the proof. Let's let delta be the larger of the two, and then I'll try to explain in the proof where we're using this. Whenever n is greater than delta, we have the following statement. So first, let's do this trick here. Let's see. Of adding and subtracting the letter y. So if I add and subtract the letter y, then I have this clever expression here of xn minus L. Right, so again, here I'm just simply looking at adding and subtracting this x sub nk. That's all that we're doing, adding and subtracting this x sub nk. Here, the nk, I'm just picking any nk that's greater than delta. I don't care which one it is, anything that you want, right? So once I do this clever trick, now of course we use the triangle inequality. So now we're just going to break this up into 2. Now on the left, I see that this here is less than epsilon prime, because remember that we have a Cauchy sequence. So this over here on the left has to be less than epsilon over 2. This works because I'm assuming here that everything is greater than delta 1. Really, everything is greater than delta, which itself is greater than delta 1. All right, so let's just let capital N be capital N sub k. Okay, so again, I'm using the fact that I have a Cauchy sequence to do this first half. Now, we can move here on to the second half because we have a convergent subsequence. So now this part should look here like epsilon over 2. All right, so again, this was the second observation that I have here, a convergent subsequence. And this now uses the fact that my n sub k is greater than delta, which in turn is greater than delta over 2. Right, so I've gone far enough out in the sequence that I don't have to worry about things. Right. So now I just put these two together. Now just add epsilon over 2 plus epsilon over 2 to get epsilon. And so now I can conclude that xn minus L is less than epsilon whenever n is greater than delta. So my sequence must converge to the same thing that my subsequence converged to. Now, I just want to emphasize here that this is also going to be very similar to problem set 5. There's one of the problems that says, show that if a sequence converges, then it converges to a unique limit. And you can pretty much do it in the same way here. What I recommend is kind of look at something like this in terms of how you might do like a proof by contradiction. So if you have 2 different limits, then try to say that you would have something like this here. Maybe the first sequence converges to some limit L1, second one converges to some limit L2. You'll see that there's going to be a problem, right? But it'll be something very similar to this here. Okay. All right, so any questions so far? Okay. All right. So let me make some remarks here on what we've actually done. So actually we have 2 things together, and we've actually proven that the following are equivalent. So first, say that we have a convergent sequence. So of course what this means is, given epsilon, I can find a delta so that xn minus L is less than epsilon whenever n is greater than delta. Right? That's what it means for a sequence to be convergent. Now we just proved that a convergent sequence is the same as a Cauchy sequence. So the difference is, a Cauchy sequence says, given epsilon, there is some delta such that xn minus n less than delta epsilon, sorry, this is a typo here, it should be epsilon, whenever m and n are greater than delta. Right, so that's what it means to be a Cauchy sequence. So if you stare at this, there's really only one place where they're different, and that's here. Right, that's kind of the main place where they're different. So in order to prove that a sequence is convergent, you actually have to know what the limit is beforehand. That's the difference here. So if you want to prove that a sequence is convergent, you have to already know what the limit is. The nice thing about a Cauchy sequence is you don't need to know what the limit is. But we can prove that a limit always exists. So in a lot of cases, it'll actually be easier to prove that a sequence is convergent because we don't have to worry ahead of time, a priori, what the limit will be. There's a second remark that I want to make here, which is about subsequences. And this kind of gets into what we've been saying about problem set 5. Let me start with the bounded sequence. Let's call it A. And we know by the Bolzano-Weierstrass theorem that it has a convergent subsequence. So let's call this here B, and let's say that it converges to some limit L. Well, we've already seen that A itself need not be convergent. However, what happens if A does converge? Well, if you stare at the way we actually just did this proof, if A converges, then it must converge to exactly the same limit that the subsequence converges to. All right, so again, we have a sequence. If it converges, we know that it's bounded. By the Bolzano-Weierstrass theorem, it has a subsequence that converges to some limit L. But if you take a look at the theorem that we just proved, if A itself converges, it must converge to the same limit that any subsequence converges to. Okay. All right, so any questions here about these two remarks? Okay, I want to end with some thoughts and hopefully some discussion of some a couple solutions to a couple of problems for Friday. Well, earlier in the course, remember that we defined the real numbers in terms of Dedekind cuts. And I promised that there will be an easier way, at least a different way, of defining real numbers by using Cauchy sequences. So that's what I want to talk about today. How might you define the real numbers using Cauchy sequences? Well, to begin all of this, let me just make the following rather simple observation. Pick your favorite rational number Q. I can take that number Q and I can define a constant sequence. So it's a sequence here where every term in the sequence is this constant number Q. Right? It's like if Q is maybe 1/2, then I'll have the sequence that just goes 1/2, 1/2, 1/2, 1/2, infinitely far. Well, that has to be a Cauchy sequence because, of course, the difference in the terms is 0. All right, so again, this here is a Cauchy sequence, and moreover, the limit is the number Q. So I can associate any rational number Q with a Cauchy sequence whose limit is Q. So let me try to do a slightly more general idea here. More generally, pick any non-empty set that has an upper bound. All right, let's just call this set S. So you might want to think of S as like a Dedekind cut. Doesn't really matter. Let's just fix this here. Let me denote L as the least upper bound of S. So sorry, this here shouldn't be B. This here should be S. And let's define a sequence A as follows. What I'm going to do is choose a collection of epsilons in this way. So let's let epsilon be 1/2 to the n, where n here is going to be 0, 1, 2, 3, so on and so forth. So any natural number n that you want. Well, since L is a least upper bound, I can find an element xn where we have this inequality here. Right. That's just what it means to be the least upper bound. So if I'm given any of these epsilon n's, I can find an xn in this way. So you can see here what I'm actually doing is I'm writing a sequence. Actually, it is a convergent sequence so that the limit here is that least upper bound. So what we've just done is we've actually just taken a non-empty set and we've written down a Cauchy sequence. So now you can really see that Cauchy sequences and limits are Cauchy sequences and then these sets with upper bounds, they're going to be very tightly controlled, right? They're almost one and the same. Okay, so any questions on this here? Okay, all right, let me move on here. So what I claim is the collection of Cauchy sequences forms a complete ordered field. So instead of now me doing things like letting A be a Dedekind cut, let me let A be a Cauchy sequence. And I claim that that collection of Cauchy sequences will be a complete ordered field. Now, there are 14 axioms that we have to go through to prove that we have a complete ordered field. I'm not going to try to do all of these. Let me maybe just do one so you can kind of get a flavor of how this is going to go. And this is going to be very much related to what you're going to see on the homework. So first, let me talk about the sum of Cauchy sequences. And I think for the sake of time, I'm not going to try to do this in detail. I'll just leave this here for the notes, but at least I want to skim over how this would go. Start with two Cauchy sequences. Let's call them X and Y. And I want to prove that the sum is also a Cauchy sequence. Well, the way that we'll define the sum is quite literally taking the sequence whose terms are the pairwise sums. Right? That's what I mean by adding together two sequences. Right. So let me not do the proof right now. I'm going to leave the proof for the lecture notes because I want to come back and I actually want to do the more difficult one, which is the one for the product. Right? I think that the product you'll find to be a lot more difficult to work through. So what I want to prove to you, at least skim over the proof right now, is that if I have two Cauchy sequences, then the product is a Cauchy sequence. And the product is quite literally that sequence such that I'm taking the product of the terms, xn times yn. Okay, so to do this, remember, whenever you want to prove that something satisfies a property, you have to do these three steps. So you always start with this boilerplate of let epsilon be given. Right? You don't even think about it, you just write it down. Now, let me do some discussion here before we try to do the proof. Cauchy sequences are bounded. So I can find an M1 that will bound the X terms, and I can find an M2 that will bound the Y terms. Right? Again, Cauchy sequences are bounded. Next, because we do have a Cauchy sequence, I can find a delta where this will be true, xn minus xm is less than this. And similarly, I can find a delta so that this here will be true. I want to emphasize that you'll notice that the M2, M1, they're swapped from what you might think that they should be. All right, so again, I can find a delta 1 and a delta 2 where all of this works. Okay, so any questions here on how at least the choosing here of M1, M2. Right. Now, once I have these, let's now do some algebra. And so I'm going to write this difference in this very clever way. So here when I write xn, yn minus xm, this will be xn minus xm times yn plus xm times yn minus ym. Right, so I'm just doing this very clever trick to kind of now write this difference of the products in this way. So once I have this, then now let's use properties of inequalities. So first, of course, I want to use the triangle inequality, and then I use the fact that the inequality is multiplicative. Right, so again, I'm using two statements here. I'm using the triangle inequality, then the property that absolute values are multiplicative. Once I have that, then I realized, of course, that xn minus xm corresponds to this, and yn corresponds to this, right? Epsilon over m2, and then also m2. Similarly, for yn minus ym, this corresponds to epsilon over twice m1, and then the xm's correspond to m1. Right, so that's part of the reason why I tried to make this clever statement here. And then now, when you just kind of stare at the algebra and look at how things cancel, at the end of the day, I'm left with epsilon. Okay. So here, you'll notice that when I did all of this work up here at the top with the bound, I actually did some scratch work that I didn't show here to actually know this is why I wanted this xn minus xm to be this quantity here. That I kind of did the algebra, then I knew that here at the bottom, this is really what I wanted to happen. And so of course now I'm actually done, because now that I know that this here is less than epsilon, whenever m and n are greater than delta, then that means that it actually is a Cauchy sequence. Okay. All right, so any questions on this one here?
Can you go over again how you first say you can use Cauchy sequence to represent real numbers?
Well, so there, it's a matter of looking at the limit. So what we're trying to say is that given a real number, then you have to ask, well, what's the definition of a real number? I mean, really, we want all of our real numbers to be things like Dedekind cuts. And remember that kind of the way that we did this was you have a Dedekind cut, those all have an upper bound. The least upper bound, that was really the real number. So in our case, now what we're going to do is a little bit different. Take any non-empty set that has an upper bound. Once I do that, then I can look at the sequence that increases and gets very close to that upper bound. That's what I mean by a Cauchy sequence. So if you will, the limit of a Cauchy sequence is what I'm defining as the real numbers. Right, so I'll try to come back to say more of that next time, but kind of the rough idea is that I want to say that the limits of Cauchy sequences are real numbers. Okay, so I know this is running a little bit late. I'll be here online in case people do have questions, and then I'll open office hours up in just a little bit. But yeah, thanks for your time and have a good rest of the day then. I'll see you on Friday.
Professor, I still don't understand, like, say if you have a real number,
Mm-hmm.
say if you have a rational number, then let's say I want to denote root of 2 with a Cauchy sequence. How would I do that?
So remember that we talked about last week in detail.
Just use that sequence that we had.
Right, those are two different examples that you could use if you wanted to. Yeah, you don't have to, but those are two examples.
So unlike Dedekind cuts, there aren't a certain formula to come up with sequences for real numbers, but we can always find the sequence. Right?
Mm-hmm.
Okay.
Right, that's exactly right. So part of this is you first have to ask what is a real number, and that was kind of the weird thing. So remember that there were a couple of different ways in which you can define a real number. One is we define them as Dedekind cuts.
Mm-hmm.
And that was this really weird thing, because we spent a lot of time trying to prove things like addition and multiplication and all the rest of that. This here will be a little bit easier, because then what I can say is that a real number is simply a Cauchy sequence. So now I can add them together, I can multiply them together. I think what you're asking is a simpler question. What is it if I'm trying to compute it?
Yeah.
So with the Dedekind cut, the way you compute it is you look at the supremum. With the Cauchy sequence, you compute it by looking at the limit.
Okay.
Right, but the point is that you don't really have to worry about computing those things. You can do this in a very abstract, generic sense. And that, unfortunately, is where it gets kind of difficult, because, I mean, the question is, like, what does this mean? How do you do that?
Okay, thank you.
Okay, yeah, you're welcome.
Hey, Professor Goins.
Yeah.
I wanted to ask about like when the next midterm will be.
Let's see. Let me tell you the date right now. I don't remember it off the top of my head.
Okay.
It's supposed to be Monday, well, due Monday, April 27th.
Okay.
So I plan to pass it out Wednesday, April 24th.
Okay.
And then I'll let you have the weekend to work on it.
Okay.
Yeah,
Cool.
that's the plan right now.
Thank you.
Okay, you're welcome.
All right. Have a good day.
All right, thanks. You too.